Hello, everyone. Hello, hello. Welcome back to Science on Tap. Today is our first installment of the spring season. It sounds like we're a TV series. For the first show we have for you today, we have a great show, fantastic show. We have Dr. Steffan Bollmann, who will talk about high performance science. So let's give him a welcome.
Thank you for the kind introduction. So probably most people know me. My name is Steffan. I was here with Saskia, my wife, for 1 year at the Martinos Center. We enjoyed our time here a lot. And yeah, we're heading back to Brisbane in the next day. So I thought before we head off, I share a topic with you that really is at the core of my heart, and I find it super exciting. I sometimes call it my pet hobby because it's our little pet project. I do this in the free time, more or less. And we call it high performance science. So just what is this about? So I want to talk about data analysis workflows in neuroimaging. And I want to show some open source tools that can help us with this process and make things more reliable and easier to troubleshoot. So first, I think you might wonder, well, is neuroimaging really that complex, right? What's the implication of this complexity? And I want to start with a little bit of motivation. So first problem that I realized is scientists write software, but we are not trained in software development. So this means there will be bugs. And the problem is that they're quite tricky to find. And especially when they deliver plausible results. So here's a comic to illustrate this. So this grad student goes to the professor and asks, well, how do I know I didn't make a mistake in my computer code, Professor Smith? Well, did you double check it? Yes. Triple checked it? Yes. Quadruple checked it? Yes. Did it confirm our hypothesis? Yes. Well, then stop checking it. And I think, in this comic, it's funny, and I think it's true, right? If you have a result that you expect, well, you don't go back and check. Well, why would you? You have more things to do, right? However, if something doesn't confirm a hypothesis, you go back and you check, and you often find a bug. So we call this in software development, this is a common thing, because when you write software, you also only realize when it crashes. And people realized that if you write big software projects with this approach, you end up with pretty buggy software. So they developed things like continuous integration testing, version control of code, unit testing. And I think a lot of these solutions that were developed in software development can actually help us in data analysis as well. So also another problem that we have is we deal with very large amounts of data. So sometimes our imaging data can be terabyte sized. And one consequence of this is that we have to run on different hardware platforms. So we have our notebooks, we have our workstations, we have clusters. And this brings its own problems with it because we run on different hardware and operating systems. So one problem that comes with this was nicely looked at in this paper. And this paper looked at different analysis pipelines in neuroimaging. And they looked at how the results change if one underlying library changed. So GLIBC is the standard C library, which implements very basic math in C. And it's used by almost all programs that run on Linux, Mac. And what they found is that just an update from version 2.5 to 2.18, which is a few years, or not sure if it's a few years, it is a while between the package update. The floating point precision changed. So if you just do an exponential function, you get a difference at the 6th digit, which you think, well, does it matter? And funny enough, they found in the paper that they could produce significant differences on a group level just because of these floating point differences, because we have a lot of steps, they add up, errors accumulate. So that was an interesting finding. And yeah, in the end, due to this complexity, that I try to present here, we have difficulties in sharing our data because it's large, it's tricky, it's often vendor specific. We have difficulties in sharing our analysis pipelines because they're often hard-coded to our platform. They're Linux scripts that only run on that cluster, and things are pretty difficult. And because of this, we've seen that there were some papers that now say, oh, we can't reproduce a lot of the science that we did. So today I want to show a few things, what we can do maybe potentially better, and what can help us in this journey. So let's start our journey. We usually start, so a disclaimer, so this talk is quite imaging focused because this is my background. I hope a lot of these things also apply to MEG, EEG. But let's start with the data acquisition. And one problem there is that our raw data formats and reconstruction that we already have on the machines we're using, they are already vendor specific. And this is great because it gives us really robust and reliable software. But for example, if you want to share this data with a colleague who doesn't have this vendor, it gets problematic because you can't just give them the data, because often the reading routines for this are also vendor specific, and you're not allowed to share these. So this was seen by a few people in the field, and there was an open data format for MRI developed, the ISMRMRD format, which is based on an open standard HDF5 plus routines for converting vendor specific formats to this open format. So the idea was, okay, with this we can build up databases online and we can share data across sites. And also people came up with a reconstruction pipeline, GADGETRON, that allows open source reconstruction of this data. But unfortunately, it got a bit quieter around GADGETRON in the last year. So we'll have to see what happens there in the community. So now we have our data in a format where we can actually start doing analysis on. So now we need to think about storing this data. And most people, they just store it on a hard drive somewhere. But the problem is, if you have it on one hard drive, how do you access it from the cluster? How do you access it from cloud infrastructure? So at the University of Queensland, where we work, we saw this problem coming a few years ago, and we came together in a big group, and we built a data infrastructure fabric across the whole campus. So we basically put we connected instruments that acquire the data, so could be microscopes, MRI systems, and we connected them with a decentralized data storage fabric. So we can basically push data from the instrument to this fabric, and then it gets automatically mirrored to the system where you want to use the data. So let's say you go to one cluster that has GPUs and is specific for machine learning. This cluster then pulls automatically the data from this instrument, and it's all seamless to you. So you always have to have the same mount points, but the cool thing is that the data always gets mirrored locally to the system you're actually processing the data on. So if you're interested in setting something up like this, currently it's not yet open source, but the team behind this project is very open to sharing all the scripts they wrote and all the guidelines that they put up. So currently the system is 2 years ago, it was widely deployed at the University of Queensland. Every researcher at the University of Queensland is using it. So we're running the system at a scale that is quite impressive. So if you want to have a look at this project, it's really fun. Okay, so now we have our data stored. And now, how do we organize this data, right? So usually from imaging instruments, we get DICOM data. And so one question that came up is, how can I make this DICOM data nicely organized so I can run an analysis on that very quickly? And this is what a group of people came up with, the BIDS format, Brain Imaging Data Structure. And I'm sure I also read something about the MAG-BIDS, where people are also thinking about doing this for the MEG community. And what this basically is, it's actually quite simple. Instead of storing thousands of files, which by the way break a hierarchical file system pretty quickly because they hate a lot of files, what they do is they convert it to a format that's quite widely used in the imaging community, a NIfTY format with a JSON sidecar file. And this JSON file is necessary because NIfTY doesn't store all the information we need in analysis. So when you convert DICOM to NIfTY, you usually lose a lot of information like the orientation of the patient, the TR that was used, the echo time that was used. So all these things can quickly go. And that's why they keep them in this JSON sidecar file. So that's an idea. And then also there is a structure where subjects are in this hierarchy, and also specific files are named and in specific subfolders. So if you have a pipeline that needs an anatomical file, it always knows, oh, if I have a BIDS structure, I go in the subject folder, anatomy folder, and I pick subject 01 T1 weighted image. So it's a naming scheme to allow us an easy sharing of the data and easy analysis. And now you can go even one step further, and this is what the REPROIN guys did. They even went and changed the names on the protocol, the protocol names on the scanner. So here on a Prisma, Siemens Prisma, where they change how they set up their studies and they change the names of the sequences they run. And then they provide a full pipeline where they go from all the DICOMs they acquire in that center to always automatically to convert it to a BIDS structure. Good, so now we have we have a data structure that we can run analysis on automatically, which is great. So now we want to keep track of what happened to our files, because often we do something on the terminal, we change a file, and here I just picked a very simple example. We have a brain, we do a brain masking, and we apply it to that. And the problem is often you want to try different things and you want to know what happened to your data. So this is called data provenance. And if you want to do this, there is one format that can do it already inbuilt, which is MINC. MINC is like Nifty. It's a file format for neuroimaging data. And it has already, when you run a processing on this file, it will always keep a history, what happened to this file. So you always know what changed your data. The problem is MINC is not so widely used anymore, and not every tool supports it. So most people still use Nifty. So what do you do if you have a Nifty file? Because it's doesn't have data provenance in there. Well, I think most people are already familiar with Git. Git is a way of versioning your script, your source code. And you can also do this for data, which many people don't know. It's called Git Annex. The problem is with Git Annex, it's pretty difficult to use out of the box. So people went and did a tool called DataLad. And DataLad is basically a wrapper around Git Annex, and it abstracts that all very nicely. So you can also manage arbitrary big files that you have and keep track of what happened to these files. Okay, now we can do our analyses. And as I said, we probably have to run on different hardware. We have to run on our notebook, workstation, cluster, cloud. And what is a good way of achieving this? And probably some people have heard about Docker. So Docker is if you think very simply about it, it's basically a small virtual machine. So in the old days, we had virtual machines and we just ran them up, did our analysis, and then we could package them and ship them. The problem were that these virtual machines are easily multiple gigabyte in size. And Docker basically took away a lot of this overhead that you need for a virtual machine, build a lot of these features into the Linux kernel, and then runs it in a very small, lightweight container. So now what this enables us to do is it allows us to package a whole analysis pipeline in a few tens of megabyte. And there are also quite nice tools with that. One tool I want to highlight is NeuroDocker, which basically builds an image for all kind of neuroimaging analysis pipelines, ENS, FSL, FreeSurfer. It packages all of these, and then it can also run an analysis through it. It can trace the execution of the binaries in there, and then only ship the binaries that you actually called from. So that's a quite nice way. So that's what I meant. This tool is called ReproZip. And then there's one problem that if you have everything run in Docker and you want to run this on your high performance cluster, your administrator will say, we're not allowing you to run Docker on our cluster. Because Docker does a lot of other things as well. It's quite powerful. And with this power comes great responsibility. And the problem is that you end up with security problems in a shared high performance computing environment, because you can actually do very nasty things inside a Docker container that would then influence the workload of all the other users on the workstation you're on or on the cluster. So there is a very nice tool that came up in the last year, which started as open source. It's still open source, but they also found a company around it. So you can also buy this now professionally with support. And it's basically compatible to Docker. It reads a Docker image and it runs it on a high performance cluster well, by design, without security implications. They had a few security bugs. They always fixed them very quickly. So the administrators are usually very happy to install Singularity on the cluster. And here in the Martinos Center, we have it on all workstations, and you can already use that out of the box and can basically pull Docker containers and run them on the cluster. So this now allows us to build an analysis, for example, containing FSL and FreeSurfer on our Windows system. We can then run exactly the same thing on our workstation. And then if everything works, we can ship it to the cluster, run our whole 1,000 subjects, and done. Good, now we have all these nice pipelines. Now we want to publish these pipelines. So what options do we have there? And I picked one tool that I quite like. It's called Boutiques. And what it does is, you see, it tightly integrates with a lot of the things I already mentioned in the talk. So it has this container, it has repositories in there, and it allows you to describe an analysis pipeline with, these are the things I want, these are the inputs, these are the outputs, and then you can run these pipelines and publish them as well under a descriptor, under a digital object identifier. So it can be always seen what analysis ran. Okay, with this, I'm running out of time. And yeah, just as a summary, I hope the whole process of neuroimaging is now a little bit more transparent to you, and you see that there are some tools to make our life a little bit easier. And I hope that some of these tools will be useful to you. And with this, I thank you for your attention, and I'm happy to chat more about all these things over a beer. Thank you.